Thank you very much for the invitation, and thank you for the introduction, Philip. So, as you said, today I will talk a little bit about volcanoes, and in particular about volcanoes as a resource. I split the lecture in several parts. I will talk a few kind of general slides. I will introduce a few general slides, and then I will talk about volcano resources. And the second part of the lecture will be focusing on volcanic particles in agriculture and gardening. We'll look at Indonesia, we'll look at the Canary Islands, and also what I think could have quite some potential in the future to reduce global hunger and also solve some of our environmental problems. So, but let's hop in. Most of us hear about volcanoes usually in a negative way. When volcanic eruptions happen, like here in Etna, which is still ongoing, it started in February and it's happening right now as we speak. And usually people are worried, people are are aware of the risks, the dangers, and it's usually associated with negative connotations. And here's some older images from Hawaii and Etna. So lava and eruptions can, of course, affect your environment if you live close to a volcano. And here at Etna, people were trying to block the lava flow. And if you have followed the Iceland eruption, people are building walls in order to stop the lava. And this often gives the impression to the general public that volcanoes are only bad. And I'd like to make a point today that volcanoes are actually anything but bad. Volcanoes have probably more good sides than bad sides. It's just that we are not always fully aware of that. So, and to emphasize the bad aspects a little more, I'm showing some pictures here from Indonesia. This is the Merapi eruption of 2006. This was in central Java, and there was a little village close to the volcano, about 6 kilometers away. And as you see, the village was almost entirely buried by volcanic material. And this, of course, makes the news, this makes the media, and it gets a lot of attention. And quite rightly so, to be honest. We need to be aware of the volcanic risks and the hazards, and we need to prepare for those. And so I'll say a few words about that. So here, just to emphasize this negative aspect, it's known for many hundred years. Here's some ancient Japanese drawing of a big eruption. And I don't read Japanese, but it says you have to be careful when the volcano erupts. And it led to all sorts of cultural phenomena, like here in Indonesia, there is people doing special dances in order to calm the volcano down. Or you might have heard of Pele, the goddess of Hawaiian volcanoes. Apparently, if you throw gin into the crater of the volcano, she gets calm and will not erupt anymore. I don't know whether it works, but people have developed all sorts of strategies in order to try to stop volcanoes from doing bad things. And here is kind of the different types of problems that volcanoes cause. I'm going to say a few words about that. So we have different timescales to consider here. There's, of course, immediate effects, and that is eruptions like lava or pyroclastic flows. This is hot, glowing ash clouds, if you will, and they can happen rather instantaneously. Then within hours to potentially days, we could have secondary effects like tsunami, as we had in 2018 at, for example, Anak Krakatau in Indonesia. And then we could have ashfall. This can go on for days and even weeks. And this may be problematic for infrastructure, for respiratory health problems, things like that. And of course, there could be long-term effects, like there could be a volcanic winter, or temperatures might drop. And you all heard about 1816, the year that kind of had all these climate problems. And there, the crops didn't ripen in the summer, and it led to all sorts of major problems because there was a big eruption in Indonesia just a little bit earlier, and it did actually have effect on climate for several years after the eruption. So the different types of eruptions, just very briefly. We have Plinian eruptions. That's the biggest type of eruption that we have. And this is these kind of columns that rise up into the atmosphere for several kilometers. And they are also, from a climate point of view, the most dangerous ones. Then we have Volcanian and Pelean eruptions. These are a bit smaller, and often they have a directed blast of ash and gas. And then we have the more harmless eruptions like Hawaiian type eruptions or Icelandic eruptions. And as you've probably seen, the current eruption in Iceland, it's more of a tourist spectacle than a serious kind of problem. And this is because there is no big explosive eruption associated with the vent or the fissures that bring the lava up. And for most part, it's calm outpouring, even if there's a bit of a fire fountain, but it's not really too serious. And here on the right-hand side, there's a little kind of sketch on explosiveness, and the Iceland and Hawaiian style eruptions are usually quite small, and the Plinian eruptions, that's the big problems that we have. So direct hazards, therefore, are big eruptions, big explosive eruptions producing these large Plinian eruption clouds, but also lava, of course, and collapsing volcanoes, landslides from volcanoes is an issue. And we could have secondary effects like mud flows. When there is a lot of snow, for example, on the volcano and it melts, it can yield mud flows, and they can also travel along river valleys for quite some distance, and therefore they can have some negative effects as well. So how do we predict eruptions? Well, the issue is that we like to think of volcanoes a bit like a patient in a hospital. You can monitor the patient and you can see whether the patient gets worse or better. And for that, we usually look at seismic signals. We also look whether something is swelling up, whether it's expanding. We look at gas emissions and whether they are changing, and also heat flow. Is the volcano getting hotter or not? And if we have several of those parameters changing simultaneously, then we need to think about the volcano perhaps erupting. And this allows us to make some sensible predictions. And if a volcano is well monitored, eruption monitoring teams are usually quite good by now to tell when a volcano will erupt. Nowadays, we also do a lot more remote sensing. So there's satellite surveillance of volcanoes. And I don't want to go into details. If you have questions, we can discuss this later. But there's a whole set of equipment that's usually deployed on volcanoes. And that tells you whether your volcano is at unrest or whether it's actually calm and dormant. And usually volcanoes show signs of change several weeks before a major eruption. So there is, in normal circumstances, time for evacuation and for taking some precautionary measures. So, but I want to talk about the positive side of volcanoes today, because I believe volcanoes get a lot of bad press already. So here, volcanic resources is one of my main interests, and volcanoes and their underlying magmatic process are the principal agents of redistributing materials within planet Earth. And this is a fundamental realization. They therefore, they are a key feature in our understanding of how we concentrate certain materials like metals, like minerals, like fluids. And therefore they are crucial for us humans that we are living on the surface of the planet. So I'll start with a little list here. So these are all the things that volcanoes do for us. And they bring metals. Most metals are actually from volcanoes. And they bring a lot of gemstones. Nowadays, we're producing sulfur as a byproduct from the manufacturing of oil. But in the old days, sulfur was exclusively from volcanoes, from gunpowder to disinfection. Building materials are often from volcanoes, abrasion materials, and of course, geothermal power. And I'll say a few words about food and agriculture later on. And if we have the time, we could talk a little bit about climate effects of volcanoes as well. So, but one of the things I didn't list is that volcanoes are actually a beautiful way to look inside our planet, because Jules Verne described in his famous book Journey to the Center of the Earth that Professor Liedenbrock was climbing down into a volcano on Iceland and eventually came out in Italy, implying that there's a system of channelways under the earth. Of course, we cannot go there, but we can use lava that comes up and we can explore what must be happening inside the earth. And people have speculated about this for many, many hundreds of years. So here's an image of Athanasius Kircher from 1664, picturing some fire inside the earth. And we have the surface eruptions. This is on Iceland in the 1970s. That's the Heimaey eruption. And if we look at the lava and study the chemistry, we can learn about the processes inside our planet. So much of our knowledge from what happens inside planet Earth actually comes from volcanoes. But I mentioned ore deposits, and I think I cannot stress this enough, that most metals that we have actually have been concentrated by volcanoes, have been brought up and concentrated by volcanoes. And here we have some images, and this is Sweden. And Sweden has the biggest iron production and iron reserves in the EU. And they are usually old volcanoes that have concentrated the iron here. And there's some of my students, when we were looking at some of the old mines here in Sweden, and several in central Sweden are no longer active, but some of the biggest mines in Europe are actually in northern Sweden. And there's active mining for iron, copper, and several other precious metals. So here is a sample of copper, gold, and silver in its native form. And this is what you get from volcanoes. Only volcanoes can bring that together. So, and most of the metals we use for construction, for our infrastructure, for our IT applications, they come from volcanoes. Most copper comes from the Andes, for example, and similar places, and they're concentrated in volcanoes in porphyry copper deposits. And iron is still the main metal. There's a lot of talk about rare earth elements and things like that, which we need for green tech and high-tech applications. But iron is still the metal number one. We need it for making bridges, for making skyscrapers, for making cars. It's so amazingly popular. We will need huge amounts of it. And this is often a volcanic deposit that we're sourcing it from. So several of the more new metals, if you will, those that are important for new technology, for solar panels, for batteries and things like that, they have also links to volcanoes. This is an image of a manganese crust, and manganese is very important for green tech. And this is from a submarine volcano in the Canary Islands. And there you get this dark layer of material sitting on top of the volcanic rock. And this is from a Geomar dredge cruise that I participated in a few years ago. And there you have volcanic dust that settles on these rocks. And this has a lot of cobalt and manganese, some of these really rare metals that we have far too little of. And volcanoes are concentrating it. So maybe in the future, going into these submarine deposits may be a way of satisfying our need for those elements. Now, having mentioned precious stones, I mean, we must realize that most diamonds actually come from volcanoes, and a lot of other fancy stones come from volcanoes. And here I have shown, or I'm showing several types of crown jewels, and they have big diamonds. And well, you all probably know diamonds come from kimberlite pipes. It's a special type of rock, and the biggest ones are in South Africa, but also in Australia and places like that. And there we get these wonderful big kind of carbon aggregates that under pressure form diamond. And diamond is super hard. We use it industrially, but we also use it as a gemstone for jewelry. And once it's cut, then they look rather wonderfully shiny. But well, as you probably heard, usually there's also a negative kind of curse or something like that with the big diamonds. So I guess it's designed to make people not so greedy. Now, having said this, I think we must realize that some of our oldest tools for mankind also go back to volcanoes. And here, obsidian, volcanic glass, has been used by humans as long as we can think, as tools, for example, and places where iron, for example, or metals were not known prior to European conquest. People were using obsidian, like in New Zealand or on Hawaii, or for instance, in the Canary Islands, people were using obsidian to make blades. And this is still very, very popular today. Some surgeons still prefer obsidian to actual metal blades because obsidian is super sharp and makes a very clean cut, and it heals a lot better, some people say. So you might find that some surgeons prefer obsidian to steel blades to this day. So, and here's just a few examples from Turkey and also from Central America about ancient cutting tools made of obsidian, of volcanic glass, because it splinters in this really sharp way, and people have been exploiting this feature for hundreds to thousands of years. Now, having said this, I think we also must accept that volcanic material is widely used as abrasion material. It's less glorious, but we're using it in industrial applications as well as in human hygiene applications. So pumice material it's highly porous, it's high silica, so it's quite tough, and it's often glass rich. And this is very good for scrubbing things. And you will actually find that a lot of cosmetic products have volcanic material in them. So here, if you look at the small print in the top left, it says ground pumice stone is part of this body care product. And several of these products here have pumice stone as a fine kind of material in there. And there's even a Krakatoa body scrub. It's going to help to remove old skin. And this is effectively just volcanic rock, finely milled. And in fact, if you have a toothpaste that is supposed to make your teeth very white, you will actually find that there's usually a little bit of pumice in there as well. So some of you will get in contact almost every day with pumice, and therefore with volcanoes. You might not even be fully aware of that. So, and if your jeans that you're wearing has a stone washed kind of element, if it's worn out a little bit or so, usually this is done with pumice stone. Stone washed jeans comes from pumice stone. They tumble it together with volcanic rocks, and it grinds down the material. So here also your clothing might have touched volcano at some point. So having said this, we all eat from plates usually, and this means porcelain. And porcelain is also made of different components. It's usually made of granitic rocks, subvolcanic rocks. So here we have quartz and feldspar, and I'm showing a big feldspar in the lower left here. And you also use clay for that. And if you mix this together, it makes this paste that you can then kind of model and burn. And it took many hundreds of years for us in Europe to work out how it's done. The Chinese were a lot quicker with that. And by now, there's many, many companies that, of course, make porcelain. And it's very hygienic because you can clean it. And this is a real advantage over, for example, wooden plates and things like that. So it's still widely in use. And of course, nowadays we make tiles and things like that because we can actually clean it effectively. Now, I mentioned sulfur earlier, and up to about 100 years ago, when sulfur started to become a byproduct from oil refining, and particularly since environmental regulations in the 1980s became more stiff, and a lot more sulfur had to be taken out of petroleum, we have loads of sulfur from fossil fuel production. But prior to that, sulfur had to be mined. So gunpowder had volcanic sulfur in it. And as you might know, if you are having, for example, wine in barrels, you need to disinfect the barrels once a year. And for that, you also use sulfur. And this is still widely used. So I found this product here from China, the Shanghai sulfur soap. It's very good if you have bad skin, apparently, then you can use that. It cleans up your skin. And if we are going off fossil fuels in the next, I guess, 50 to 100 years, we will actually run into a new problem. We will have to quarry sulfur again from volcanoes because the byproduct will also not be available anymore. If we don't produce fossil fuels anymore, then we might need to go back to quarry sulfur. So here's some sulfur mines that are still active in Indonesia on the left-hand side, and the top right is an old abandoned sulfur mine in the Andes in Chile. And several of those will have to probably pick up more production once our electrification of the traffic has progressed a little bit further. So now geothermal power, this is something that is very popular, and Iceland, for example, has a lot of very cheap energy because of the geothermal power, but also countries like New Zealand, like Indonesia, like the Philippines, they also can harvest geothermal power. I now heard that El Salvador is doing Bitcoin mining with volcanic clean energy. So, and they have just admitted this as a legal tender, and they believe they don't harm the environment because they use volcanic geothermal energy, which is kind of happening anyway. And this is the concept of a geothermal power plant. In the top left, we are close to a heat source. Water gets heated up, it converts to steam, and steam expands in volume, and then it will rise up and we can drive turbines with it. Or if you want, you can even use it for direct heating. In Iceland, for a long time, geothermal waters were used for direct heating. And when I remember back the days when I first visited Iceland, I was in this hotel in Reykjavik and I opened the water tap, and suddenly there was this smell of sulfur in the room, and it was actually volcanic heated water, and they didn't kind of clean it. It was just there, and it was a bit of an awkward smell, like rotten eggs. I didn't feel it was particularly pleasant. They have now changed their system a bit. They still use it for heating this water, but they don't use it for hygienic purposes anymore. But I should say that there's a lot of metals and other substances, minerals dissolved in geothermal waters, and the pipes clog up very quickly. And there's an image in the lower right-hand side from New Zealand. This is a clogged up pipe after a few months of geothermal fluids running through these pipes. They actually get tighter and tighter. And what the people in New Zealand do is they take the materials in there. There's actually a lot of silver and gold in there. And this is a very useful resource as well. Now, here's a few impressions. This is a big power plant in Indonesia, a geothermal power plant in West Java. And here is a few more impressions from Iceland. And you might or might not know the Blue Lagoon, which is a big bathing spot on the Reykjanes Peninsula. It's actually a byproduct of the geothermal power plant there, which is the main power plant that supplies Reykjavik. So all the extra waters are kind of put into a basin, and then people go bathing there. So it's actually kind of wastewater, if you will, but it's full of these minerals, and therefore it's very healthy. And here, as you might see, a lot of electric energy is generated on Iceland. And then there's a few other things. Greenhouses are heated with that. And Iceland actually produces more bananas than most other European countries because of this free energy that the volcanoes bring. Now, this is at the Blue Lagoon. Last time I was in Iceland, I couldn't help but take a few pictures. They're selling the kind of minerals that are dissolved in the water from the geothermal power plants for cosmetics because they're good for your skin. And they're selling it particularly to Asian visitors. They seem fascinated by this concept. So here, a lot of people would actually use cosmetics that comes from volcanoes. Having said this, I'd like to talk a little bit more about the minerals that are dissolved in waters, volcanic waters. And this is likely to be very, very important for us in the future, because what we need for electrifying the traffic is one particular element, and that's lithium. Lithium is very kind of soluble in hot water. And this is why a lot of the waters in the Andes, where there's a lot of volcanoes, they have a lot of lithium. And in the Atacama Desert, where these pictures are taken, where the water then evaporates, you get these salty crusts. This is not snow, this is all salt here in these images. And these have a lot of lithium and boron, which we need for making batteries at the moment. So a lot of it is harvested there. And here's a few more impressions how it's harvested. And they have these large salt lakes. And it's a renewable resource in the sense that more and more of this water is expelled and evaporates and produces things. But one problem is that if we over harvest, we will reduce the groundwater table in these areas. And many of the local indigenous communities are not very happy about that because the Atacama Desert is very dry. So if we are artificially depleting the groundwater level, then these local populations might actually get into trouble down the route. But we need something on the order of over 900% of the lithium that we are currently producing. So it's almost unthinkable that we cannot mine these things. We will have to quarry them if we want to electrify the traffic until 2050. Huge amounts of this will be required, and it's the volcanoes that are producing it. So this is the key point I wanted to make. For electrifying traffic and many other IT applications, we need these elements. And while on the one side, there's a lot of opposition to mining and quarrying, on the other side, many of the new green tech applications require metals and elements that come from volcanoes, and we will have to go and get them. But having said this, I'd like to say a few words about volcanic stones as well. And I guess one of the earliest forms of our use of volcanic stone is to actually dwell in it. And here's a few images from the Canary Islands where people have made caves, and this particular one was probably a grain store and not something to live in, but people have made these little shelters and stored grain in there prior to the days where we had you know, the infrastructure to store this properly. This is high in the mountains. It's very dry. It's sheltered from rain. So it was easy to protect because there was only one way to get to it. And this was likely a very efficient grain store where surplus from harvests could be stored for years that were less good in terms of harvesting. So here people have managed to actually get by over not so good years by using volcanic rocks for storage purposes. And of course, they also lived in it. And here's some of these caves. This is called the King's Cave, the one on the left. And I went inside. It's kind of spacious. I mean, it's fair enough to live in, I guess. And some of these caves have been converted to restaurants. That's the picture on the right-hand side. So you can actually go inside and have a meal there in the Canaries. So this is almost a tourist attraction, but the caves go back to pre-Spanish times. Now, this is Cappadocia in Turkey, and there we have seen for a long time that people have been dwelling in volcanic rocks. It's easy to carve, and people have been building on volcanic rock. And here's a few examples from Scotland, from Austria, and from France. Volcanic rock weathers very badly, and therefore it often sticks out, and then you can build something on top of it. And the Romans have pioneered this. They have started to make cement from volcanic materials that are particularly chemically reactive, and therefore they have built rather wonderful architecture with volcanic stones and the porcelana cement. Now, volcanic stone has been used in many, many cultures. Here's a few more pictures from Indonesia, and here some of the temples in central Java around Merapi volcano, and they're all built of volcanic stone. And this goes on. Here is a little church in Arico village in Tenerife, and this is quarried close by from volcanic rock that has erupted from the volcanoes in Tenerife, and this is still used today in many of the building applications on the Canary Islands. It's a very popular stone because it has little vesicles, it has bubbles, so it's good for insulation, but it's not too dense. So, and this is true, of course, in other parts. Here in France, in Clermont, we have volcanic stone, and in the Eifel, the volcanic district in Western Germany, there we also use a lot of these volcanic stones, and they are good for building tall buildings because they're not too massive, and at the same time, they're very sturdy. This, of course, can be used for grinding purposes as well. This is a form of abrasion, if you will. Millstones from the Eifel have been sold all over Europe for many hundreds of years. The Vikings imported millstones from the Eifel, for example, and you can see in the archaeological record that it wasn't perfect for their teeth. It also grinds down your teeth if you have too much of it in your food, but it's certainly effective to grind corn and other cereals. So here, as a cladding stone, volcanic rocks are extremely important. And then I'd like to move on. As a concrete supplement, as an aggregate, it's also extremely important. And the top image is in Indonesia, where people are quarrying volcanic particles to put into concrete, and also on the fields. And then there's some houses here in Las Palmas in the Canary Islands. And they are made from Portland cement that has a large proportion of volcanic particles in it. So I would say about 30 to 40% of this image is actually made of volcanic particles, although you don't see it immediately. So here's a few more impressions. And a good thing here is that when they quarry this in Indonesia, they also create these uneven surfaces. They quarry this purposefully chaotic, so that if there's new material coming from the volcano, it creates a sediment trap. It will slow down lava or ash clouds when they travel over this irregular surface. So here they get the material, and they can actually ensure that the next eruption will be a little less problematic. But now I want to talk a little bit more about agriculture and gardening and volcanic particles there. So we've talked about primitive housing, concrete supplements, abrasives, and the focus now for the rest of the talk is agriculture and gardening. And let's start here. I guess most of you have seen this. There's a bottle of wine from the Auvergne. It's the Cuvée des Volcans. And then there is a bottle of wine from Etna and several bottles of wine from the Canary Islands. All of these have grown on volcanic soils, and they are supposed to be particularly fertile because they have a lot of nutrients. And this is Merapi volcano in Indonesia. And close to the volcano, of course, it is dangerous. But a little bit further away, the soil is extremely fertile, particularly if you have moisture. And in the tropics, there's a lot of water. So it's super green there. You can grow all sorts of exciting things there. And on the left, you see rice paddies, which is the most dominant food in Asia. It feeds most people. But you can also, of course, grow a lot of exotic spices. And no big surprise, many of these exotic spices come from Asia because they have the climate to grow them. So then I should point out that coffee is very important in Sweden, certainly. And I should say that Sweden is amongst the highest coffee consumers on the planet, next to Norway and Finland and Iceland. I think it has to do with the lack of sunlight. The less sun you have, the more coffee you drink. And so we must realize that something like 70% of all coffee is grown on volcanic soil. So this is really, really dramatic. So when I drink coffee here, I'm in contact with volcano, if you like. And here's some images from coffee plantations in Indonesia. And here's some coffee beans. And well, they are kind of not very aesthetic when you harvest them. And then you roast the beans, and then you grind it up. And that makes the coffee powder that we consume. Now here, chocolate is also grown on volcanoes. This is a chocolate plantation in Indonesia. And here the cocoa beans are harvested. And again, they need a special type of climate. And chocolate is not exclusively, but a lot of chocolate is grown on volcanic soils. And here is quite a number of chocolate products that I found that actually built in their advertisement on these volcano things. The most famous chocolate in Iceland is called lava, for good reasons. And Here we kind of see that some companies exploit this connection. Tea is no different. Tea is also grown a lot on volcanic soils, and tea needs a special climate. It needs high altitude, it needs cool kind of climate, a lot of water, and usually volcanoes provide this. Here I've got a very special plant that is also grown on volcanoes. Maybe you know the plant, maybe not. On the left is the young plant, on the right it's the flowering plant. And if it grows more mature, it looks like on the right-hand side. And if it's fully mature, it looks like this. And once it's harvested and used, it looks like this. It's tobacco. And tobacco is also grown a lot on volcanic soil. Winston Churchill's cigars were grown on La Palma. And nowadays we have less smoking habits to feed. So what we do usually is we use nicotine as a fertilizer and for medical purposes. So tobacco growth is not getting less, surprisingly. We just use the material for other purposes, less for smoking, more for medical purposes. So now this is all easy when you have water, like in the tropics, but what do you do if you don't have water? And this is where I want to move to the Canary Islands now for a little while. And here in the Canary Islands, there is not a lot of water, but a lot of volcanic rock. So, and here is a bit of a climate map, a climate classification. And as you can see, the orange colors are very dry. So round about the mid-latitudes of our planets, things are very dry. This is where the Canaries are located. And this is the landscapes we see there. They're almost desert-like and only close to the coast. We have a few ponds, but inside the islands, it's super dry. And this is, of course, problematic. The initial settlers had real problems. The initial Spanish settlers had real problems. And there was this strange eruption in the 1730, and it lasted for 6 years. And it was on Lanzarote. And the Spanish king sent a bishop, Bishop Davila, to monitor the eruption. That was his kind of most educated person he had. And he ordered that all the people had to be evacuated. And he stayed on the island to observe things. And he made this rather fundamental observation. He looked at lapilli, little stones from volcanoes. And when there was a thick cover on the fields, the plants died. But if there was a thin cover of lapilli, the plants flowered and they were blooming. So he realized that there's something going on. And the eruption lasted for 6 years, as I said. A quarter of the island was covered with lava and lapilli stones. And once the villagers returned, they had these kind of devastated fields. But the bishop recommended that people distribute lapilli stones all over the barren fields. And this is still used today, and it actually allowed to grow a lot of things on the island. So here we see wine production on the Canary Islands, even though there's a very dry climate. And here's a few more kind of impressions. And you can actually make the situation much more bearable in even a dry climate with these volcanic particles. And it allows to have vineyards, and this is a major tourist branch now. It's a major income branch these days in the Canaries. And here you see large fields being kind of covered with these lapilli, and they have this special way of growing the wine, these kind of little depressions where the wind is going over. It protects the wine plants. And the population doubled in the decades after the eruption because of this invention. And suddenly they were able to grow potatoes and fruits and wine, which they weren't able to do beforehand. And it went as far that the wine got so famous that at the Vienna Congress in 1815-16, it was Canary wine that was drunk. That's still, you can still read it on the menu. So Lanzarote wine is starting to become famous again, and it's very popular. As I said, you can go and have a bodega holiday there, and it's rather pleasant. But there's some downsides to this, and that is that they use the lapilli from these little volcanic cones, and of course it wears down the volcanic cones. So here we have some open scars. The problem with this is you need to quarry the material. Anything we take will leave a gap behind, and this is unavoidable, unfortunately. So I visited some quarries here, and Harri in the audience, he was with me at the time. And here, this is on Gran Canaria. This is a big quarry on Gran Canaria where they separate the lapilli. They call it picon locally. And part of it is for agriculture, part of it is for gardening, part of it is for cement production. So it's widely used as an aggregate. Here's a few impressions. This is Montaña Negro, and here's a picture from 1906. And you see the volcanic cone is intact, but today it's got an open scar from quarrying. And this is one of the downsides of the use of these lapilli. So there is no kind of making it go away. And here's a few more of those sites where there's open scars in the landscape. For geologists, this is exciting because you can look at the rocks, but for most regular people, this is actually less attractive. Now, a few kind of impressions from Tenerife. Tenerife has a lot of vents that are distributed along these three main axes of the island. And there's an impression of the 1798 eruption in the top left. And if you have the weather side of Tenerife, the northern side, and you add these lapilli to the soil, you can grow a lot of crops. And this is why the Spanish were interested in the Canary Islands already in colonial times. They were growing all sorts of things, bananas and wine there. And this is quite tropical there if you add water and volcanic soil. Now, in many parts of the island, you can quarry these materials. There's loads of it there. If you accept that there will be some scars, then there is no shortage of this material, really. And you can take different types. And in southern Tenerife, they use the white pumice, and in northern Tenerife, they use the dark lapilli, but both can be very useful in agriculture. And here's some more impressions of how it's used. And there we see some of these cones that are only half there because the other half has been quarried away. There's this rather intriguing case of Humboldt's three cones. Humboldt visited the island in 1799, and he describes three cones in the Orotava Valley. And apparently they were so beautiful, he says in his diary, that he was touched to tears. If you go there today, there's only 1.5 cones left because the other 1.5 have been actually quarried away, unfortunately. So I'd like to take you to La Palma for a few minutes now. There's frequent eruptions on La Palma, the last one in 1971. And there people are using this concept now really widely. And this is some impressions from the 1971 eruption on La Palma. This is some of the lapilli deposits on top of the crest of La Palma. And here's some of the lava flows that have come down, and you see that they were going all the way down to the shore, and they formed these lava platforms. And as you see in the image to the left, there's a lot of green on these lava platforms, and this is greenhouses and fields that the local people have put there. Because it's warm on these coastal platforms, they add a lot of these volcanic particles and a bit of soil, and then they can grow bananas, tomatoes, pineapples, and all the rest. So many of these coastal platforms, they are now used for fields, and you see these white kind of boxes, if you will, in the lower image here. All of these are greenhouses on the very young lava platforms. So here's in the top left an image from 1949, how one of these lava platforms formed, and by now it's full with fields. And this is the same for many of the other lava platforms, including the 1971 platform. So here we can see that you can make arable soil and land that you can use for agriculture rather swiftly if you use these volcanic particles. And as you can see, they're quarrying on top of the island here. This is La Palma, and they're bringing it down to these coastal areas on the platforms, and bang, they go green. So what is the power of pecan? What is the secret behind it? I mean, one of them is that moisture is trapped inside. The vesicles inside these little particles, they allow water to condense. And in the Canaries, we don't have a lot of rain, but we have a lot of clouds. This was already described by Humboldt. It's called the Sea of Clouds. And here's a sketch from Humboldt on the left. And he has this corona, this rim of forest on the slopes of Tenerife. And this is where the clouds are actually in the morning, usually. And this is where the water condenses, and it leads to a lot of plant growth. And here you can see the Sea of Clouds from the top, from Teide volcano, the highest peak on the island. And this cloud is usually at a level of between 1,000 to 2,000 meters above sea level. And here on a Google on a Google Earth image, you see this green strip. This is where the clouds come in. I marked it here with red lines. And this is a crown of forest where a lot of the moisture is condensing and it forms a lot of water. There's this ancient legend from the island of El Hierro. There was a holy tree in the mountains, the Garahoy, and the local people used it to produce water because it was sitting on an impermeable layer of clay, and the water couldn't filter into the ground. So it made a little lake around the tree. And this was kind of the tree that was raining water. It got legendary status, and you can still visit it today. But all the water actually comes from condensation from the clouds. And to give you an impression of how much water can be contained in these lapilli, here is a picture from, I think it was Harry's hotel room one day during fieldwork in the Canaries, and they delivered some sacks of pecan here. And here in these sacks, it looked dry when they were delivered, but the next morning there was so much water condensing, and this was obviously inside the particles. So we looked at some of these particles with the electron microscope, and to our surprise, there's life in there. So it's not just the particles itself, there's actually a lot of microorganisms in there, and they eat down these volcanic particles. So here on the left, we have a vesicle inside the rock, and it's full of organic remains of microorganisms. And I'm not a specialist for the type of microorganisms, and I don't want to spend a lot of time with it. But once we started to look, we found that this is full with microorganisms. And I had some colleagues from paleobiology. They helped me identify many of them, and the names are there in Latin. And many of them are specialized in volcanic rocks, and they live inside these rocks, and they break down the rock. This is rather important because it means that there's a gradual supply of nutrients that's coming from the rock, and it's delivered to the soil by these microorganisms. And the more microorganisms you have in the soil, the more CO2 you bind in the soil. It's called living soil. And this means that some people estimate that if you have more of these microorganisms, you can sequester, you can bind, you can lock a lot of CO2 in the soil itself. Many soils are actually depleted from over harvesting. And if you manage to get these microorganisms back, you actually have a chance to do good for producing better yields, better harvests, and for helping the environment. So I'll spend a few more minutes on this. Here, this living soil concept is important. I am not sure how good these estimates are, but there's recent papers that say that we could potentially lock several gigatons of CO2 if we were to rigorously revive our soils. And this would be a very clean and efficient way to sequester a lot of CO2. And there is another aspect here. In addition to the microorganisms, the volcanic particles might actually weather, and they might convert. If we have calcium silicates, typical minerals in volcanic rock, and we make carbonates of them by weathering, calcium carbonates, magnesium carbonates, we also bind a lot of CO2 from weathering products. It's called enhanced rock weathering. And if this works, then we would bind even more CO2 in the soil. So there's two things. There's the organic side and the rock weathering. And those two things together could make a real difference for crop yields, as well as for removing CO2 from the atmosphere. There's a problem, however, and the Canary people were very lucky. They didn't know that. But many volcanic rocks can be poisonous. If you have too much nickel in your volcanic rock, then this is not good for your crops. But luckily, the rocks in the Canaries are kind of low in nickel and chromium and things like that. But there is some rocks that have high values of this. So let's give a little outlook for the last few minutes. And Bishop Davila, he had no kind of concept about it, but he really revolutionized agriculture. And I think we're still learning from him today. And I think there's still more we can do with his ideas. This is kind of some areas in the Canary Islands. And I think, personally, I think we can make those into fertile land if we do the right things. I could see ourselves to really produce a lot of crop farms, for example, in the future. And this rock weathering would also be a really, really useful thing. So as I said, we could potentially store a lot of CO2. And I'm not sure how good these numbers are, but this concept of adding pecan type material to soils will likely increase the microorganisms in the soil, and it will produce rock weathering. And given that many parts of our planet are very dry, like the yellow parts here on this map, and they will stay dry, and it might actually get even worse for the next decades, given the predictions of our climate, I think there will be some need to produce more food. And if you look at the Sahara, if you look at Australia, if you look at parts of Southern Africa, the Arabian Peninsula, I think there's quite some room to fertilize large areas of land if we do it systematically. So here we can, with additional moisturizing, with irrigation, we could potentially produce large crop farms that could feed a lot more people. And this is an important kind of concept as well. I don't want to go into the details of this right now, but burning fossil fuels is producing a lot of extra CO2 that's going up in the atmosphere. Nature is not taking enough CO2 out of it. And here, if we were to use consistently volcanic particles for our agriculture, people estimate that we could produce a lot of CO2 as a sequestering concept. And this is from a paper from Bierling et al. 2020, and it shows how much CO2 different countries could actually capture by putting volcanic particles on their fields. So the other notion is that those countries that produce a lot of CO2, like the States, like China, they also have a lot of agriculture. So they could actually do that quite effectively. And here, this is kind of agricultural areas, high production of agriculture in red. And Europe is, of course, very important. America, North America is very important. China is very important. And Sweden, certainly in the south of Sweden, could also do it. We have the right rocks here in the south of Sweden that could be used for this. So you wouldn't have to ship the rocks in from the Canaries or elsewhere. We would have them close by. And this could therefore be a rather effective way of doing it. Now, downsides. Very briefly, I want to mention those as well. We would need to mine these rocks. There's no way around. But I guess this is unavoidable. We have a lot of volcanic areas in Europe, in certain islands, but also in Germany, in France, and we could use materials from there. And we could therefore reduce CO2 in the atmosphere, potentially by several tens of %. And how much it will actually be exactly is something we will need to do in experiments. And we have a little campus garden here, and I have started to have a little experiment there where I put volcanic particles on a field and I left another part of the field untouched. So we'll see whether this makes a difference. but some work will be required to fully understand the potential of this. And I think if we use real rock, it's going to be tough. We need to crush it. That's energy intensive. The reaction rates will be slow. But if we use particles like this that are already kind of small, and we put those on the field, it would be a lot less energy intense. And it would save us a lot of headache and trouble. And I showed this earlier. This is really images or calculations of how much of the pledged Paris Agreement CO2 reduction different countries can achieve. So China could take 10%, the US could take 10%, India could be up to 50%, Indonesia 25%, Canada close to 40%. I think Germany is already doing rather well on the agriculture side, so there's not a lot to be gained there, but France could actually potentially get 50% of their Paris Agreement reductions via using volcanic particles on agricultural soil, and so could Spain. So this could make a real difference if used on a large scale. Now, this brings me to the end, and I'd like to first of all thank you for bearing with me for the last hour. And if you're interested, I think Philipp sent this around, our little article, our little idea article from a few years ago. Most of the concepts from the Canaries are in there. I'd like to say thank you to Philipp for inviting me. And then if you're really interested, we have a few more things in one of my books, The Geology of the Canary Islands. There's also, of course, geography and agricultural aspects in the book, and it's available on Elsevier. And I'm gonna stop now. I talked for exactly an hour, so it's time for someone else to talk. So I say thank you for your attention.